pleasure and honor to welcome Rich Zemel to the Center for AI and Society at York University, our CAIS Talks series. So Rich is an old friend of York University and ourselves, having been a professor at the University of Toronto for a long time. He's been here before several times to give talks, for example, for the Center for Enrichment Research. So I'll just give a brief biography for those who are meeting Rich for the first time. So he did his PhD, and correct me if I get any of this wrong,
sure.
With Jeff Hinton at the University of Toronto, and did postdocs at the Salk Institute and CMU. And then I believe was appointed as a professor at the University of Arizona in computer science and psychology. And then eventually moved from there to the University of Toronto to computer science. And he's now, and I'll probably pronounce this.
I don't know how to say it.
I'm going to say Triant.
That's pretty
Diacolis? Diacolis, sorry.
Yeah.
Professor of Engineering and Applied Science in Computer Science at Columbia University in New York. And he has been a very important leader in AI and society, I think, over the years. He's currently, I think, director of the NSF AI Institute for Artificial and Natural Intelligence, as indicated on this slide. And importantly for us Canadians, he is a co-founder and the inaugural research director of the Vector Institute for AI in Toronto. He is, I think, still a Canadian Institute for Advanced Research AI chair, and Amazon Scholar, and serves on the advisory board of NIPS, of Neural Information Processing Society. Has received many awards. I'll just mention a few. I actually saw you just briefly at that meeting, the 2023 CAIS Lifetime Achievement Award, presented in Montreal, where almost all of us got sick. Hopefully you avoided that.
I did.
Okay.
Yeah,
okay.
Yeah.
That's good. So
yeah.
That would be kind of a give and take away.
Yeah, right. Yeah. Nice lifetime. Yeah.
And held an industrial research chair in machine learning back in 2018 and received a Pioneer of AI Award from NVIDIA in 2016. So has made many research contributions in addition to those leadership contributions, for example, in unsupervised learning, going back all the way to his work with Jeff, few-shot learning, graph-based machine learning, and I guess more recently algorithms for algorithmic fairness and robust machine learning, which I think is probably what we'll hear about today. So
great.
Thank you, Rich, for coming.
Thanks a lot, James. Thank you. Okay, well, it's great to be here and see a lot of familiar and unfamiliar faces in the crowd. So it's nice to be here, and I like the room. It's very kind of informal setup, which is perfect. I'd like to keep the talk informal, and please interrupt me, or if you have questions or comments, criticisms, whatever it is. So feel free to speak up. I'd like to make this interactive. This is the first time I'm giving this talk, so I'll be working on the kinks. Okay, so as I say, it's steps, and I'm going to use my finger. Luckily, I don't have a pointer. So there's steps towards responsible deployment of large language model. That's the topic of the talk. So here's a question. So here's our large language model. Like, this is a transformer block inside which underlies all the big language models, multimodal models these days. And as everyone knows, it's like a complicated black box model. We don't really understand what's going on inside of it. And these days, because they're becoming so ubiquitous in all of everyday life, including high stakes applications in medicine and law and every facet of life, it's really important that these machine learning systems be what we call responsible. So I must admit, I've been at this a long time, as James said, and this didn't used to be something we cared about, right? It was like, let's build an ML system that works, that does something. And now it's a question, can we make it, it's not just that it has to work, but we have to understand it from lots of different sides, and there's different facets of it, including this idea of responsibility. So now we have to try to define this. What does it mean to be responsible? It really underlies this question, can we trust these kinds of models? That's really what we're trying to get at. So that's the topic today. I'm going to be defining responsible machine learning systems and giving some attempts to explore a few dimensions of responsibility. So the first one is that we'd like some assurances of how they're going to work when they're deployed. Okay? Some guarantee that when they're deployed, they're going to work the way we'd like them to. All right? So that's the first primary definition. So let me go through a little bit of history about performance in ML systems. So going back a ways, nowadays we base this on some, well, it's still true, we base it on some test set evaluation. In the old days, people didn't think about the training and test kind of split. You trained it on some data and showed it worked on that data. Then was the idea, well, you should actually hold out some data, test it, and see that it generalizes on some new data, right? And so back in the old days, there were these limited test sets. One familiar one was called the UCI, University of California Irvine data set. And then there's what I would call the fruit fly of machine learning research, the MNIST data set, the handwritten digits. And just an anecdote from working with Jeff for so many years, right? So Jeff would run down the hallway and tell me, I've solved it, I've got MNIST down from 8.3 to 8.1% generalization error. Right? So it was always about trying to get a little bit better on this test set. And also it was very popular to have homegrown data sets. So as James said, I did a lot of work in computer vision. And in computer vision, you're always saying, well, what kind of problem are we trying to solve? And I remember one thing we did was, I don't think I have the image here, but I remember we were working on solving motion. So, trying to come up with some models of motion that would work and could track something as it goes behind an occluder, right? And infer when it's gonna come out the other side, where is it gonna be? And to test this, I was there with my postdoc and grad student in the parking lot behind our building. We were rolling balls behind garbage cans and bouncing them and creating videos of this and then testing it. So we had our kind of own homegrown data sets that we rolled at about the right speed and bounced in the right way so that our algorithm would work. So that was very popular then. Everybody had their own data set. And then we moved on to bigger benchmarks, things that were in common amongst the things. And now it was like you couldn't create your own little benchmark that you did well on. It had to be that everybody had the same benchmark and report on the same thing. And that was really important for the field to move forward. And that's been a big step forward. But it doesn't really solve all the problems, right? So one problem is that the performance is really based on a single number. The idea in all these data sets is you hold out a bunch of data and somebody submitted an algorithm, it makes a prediction on that each held out item in the held out data set, and you test it and you look at how accurate is it and average the accuracy of all the held out items, okay? So then you get a percent correct, and it's all about competing on that percent correct, okay? And as we said, think about responsibility or things like fairness. The idea was that many metrics, suddenly we became aware that metrics beyond accuracy became important. It's not just getting it correct, but it's also how does the performance break down amongst different groups? For instance, is it getting all the ones correct for the majority and getting all the ones for the minorities incorrect? All right. So that gave rise to considerations like fairness that we've been working on for the last 10 years or so. But that never used to be something we cared about. It was always just you just average it and say what's percent correct. So now we want to have other kinds of metrics that go beyond accuracy. Another one that came up was leaderboard hacking. So leaderboard hacking was all about saying, well, you can just keep submitting different algorithms, and then you could, now what people were doing is they were coming up with 10 different algorithms, submitting them all, and then whatever one worked best, they would still get highest on the, that would be the one that they'd report on the leaderboard, right? So you could do this, and in fact, one of the companies got shut down for doing this kind of leaderboard hacking for a while, where they were trying just to sit. Because the idea was when you figured out which algorithm worked better on the test set and got a higher number, you could kind of reverse engineer what was in the test set, right? And then improve your algorithm and gear your algorithm towards that, okay? So that's leaderboard hacking. So that's another kind of problem. And now something else that comes up in these new systems that are these like large language models or language and vision models that are generating images, generating videos or text. It's not just a single number that they're predicting that you can compare to some ground truth, right? They're spewing paragraphs at a time, and how can we evaluate the quality of that, right? So what's the quality of the generative output? Right? So these are the kinds of problems that come up when we want to say, we want to see that our, have some sort of guarantee or assurance about performance. Okay. Any questions or comments about that? I'll say some more about it, but this is more of an introduction. So the second facet, I think, of responsibility is aligning with diverse perspectives. Right? So I already got a little bit into this, where the idea was we might want to break down the data set into different kinds of partitions, and think about not how well is it doing overall, but how well is it doing in different partitions for different groups, under different circumstances, right? So different kinds of partitions. So aligning with different diverse perspectives, though, here I mean something a little bit beyond that. Okay? So there's the term alignment. People have probably seen that term. It's used and abused a lot. It's not clear exactly what that means. So alignment typically means that the LLM outputs aligns with or fits with individual values and tastes. Right? So the large language model. So one kind of goal is that it should be able to follow complex user instructions. A user can say, please answer this question without being too verbose, but that with something that is not harmful, that kind of idea, right? So, and you want the system to respond accordingly. And another one is that it's not supposed to produce dangerous or offensive responses. Okay, you want to make sure that if you ask it, how to build a bomb, that it doesn't tell you how to build a bomb. Okay, so these are kind of, so alignment is many different facets. These are a couple of them. And more recently, the question was, well, how to get the systems to align with what people would like, right? So that's really what, these are the kinds of descriptions. So alignment typically means fitting with how individuals would like the system to behave. So there was the paradigm of reinforcement learning from human feedback. So just so I get a sense of it here, like how many people are familiar with that here? Okay. Okay. So the idea in that is that you take a language model, and language models can, there have some stochasticity underlying them. So for the same input, the same kind of question, they can produce multiple outputs. All right? So you get the language model to produce, let's say, 2 responses, a pair of responses, and you get a human to annotate and say which one they prefer amongst the 2 responses to the question. Right? And do that many times, many different questions, many different pairs of outputs. And now, the model is trained to output the responses that were preferred across the population of annotators, the people who said which was better. Okay, there's lots of algorithms that have been developed for this, but that's the basic idea, is that you kind of get this preference ordering of, response A is better than response B, response E is better than response F, and you train a model so that when it produces an input, it would produce A and E as outputs rather than B and F. Okay? So that's reinforcement learning. It uses reinforcement learning to train the model from human feedback. So there's a problem with that, in that this is across the population of annotators. So it's kind of averaging over all of the different annotations. So it's really, again, kind of fitting what you could think of as the majority. It's aligning with the majority, whatever these annotators are. And so it's really dependent and biased towards the population of annotators. People have studied that a lot very recently to say how the annotation population is reflected in the new models. Okay, that the overall population, the kind of demographics and those kinds of things are reflected in the trained models that were trained using this RLHF. But in general, what we'd like to do is make the model conform to a diverse set of human values and preferences. Right? People have different likes and dislikes, individuals do, right? And so they vary widely in what they would like the model to do, what their values are. Right? And so ideally, we'd have a system that can understand and cater to this broader set of user needs. Okay? It's not that it would necessarily, ideally, produce the same output for everybody, right? But you could say we would like to align, kind of steer the model to produce outputs that are more like a particular individual or a particular group, whatever it is, so have some more control over the model, okay? So that's what I think of as a second thing, which is aligning with diverse perspectives, okay? And the last kind of definition of responsibility that I'm going to talk about today is developing methods that conform to and facilitate regulation. Right? So this is again something that we never used to worry about, was regulation of AI systems, but it's becoming very important. And some people in the field really resist it, but more and more I think people are recognizing that it's important that there be some regulation of these systems, because if they're going to be used so broadly, especially in such high stakes domain, that there should be some regulation, some sort of oversight of how they're used and their performance, okay? But I think it's not something where we can just throw the system over the wall and give it to the regulators and it's up to them, right? So I think there has to be some work that goes on between the people working in AI and the regulators and try to say, how well do the AI systems, how amenable are they to regulation? And how can we develop systems that are more amenable to regulation, okay? So that's a third kind of responsibility. So those are the three I'm going to focus on today. I think there are other aspects of it, so maybe at the end you can think about if you have other aspects, and we could talk a little bit at the end about things that other kinds of responsibility that are important. So just to say more about the regulation, just to give you an idea what I mean in this case, there's been a lot of studies of discrimination, like a lot of the fairness work focuses on the standard machine learning paradigm of classification. Right, so classification, you have an input, and it produces a prediction that's like a discrete prediction, the standard thing, is it a dog or a cat or whatever, that's one kind of classification. Another one, or more importantly, when it comes to regulation, decisions about allocative decisions, right? So things like, who's gonna get a job, is this person gonna get the loan or not? Allocation of resources, okay? So if the system predicts who's gonna get a job or who's gonna get a loan, that's when discrimination comes up. Right? And that's when the fairness considerations kick in. There's the doctrine of disparate impact in the law that says there can't be unjustifiable disparities in allocations across different demographic groups. Right? So that's the legal regulation. And the nice thing is that's a nice clear law that we can then operationalize, right? As computer scientists, you can then turn this into some mathematical formula and test that mathematical formula, some sort of metric or evaluation for your classification system. So that's what the field of fairness is all about, right? So we had a paper, one of the original papers in the field some 10 years ago, where we proposed some definitions of fairness. Like there was an individual kind of fairness and a group-based fairness. There's notions of fairness, and they all had some mathematical underpinnings. And they got at this different ways of interpreting what this means, right? And then, there was a proliferation of definitions. There was a paper, I think, called 21 Definitions of Fairness that came out a few years ago, right?
Are they consistent with each other?
No, so that's a good question. So, no, they take different considerations into account, right? So the typical one, so just to give you an example of the standard ones is demographic parity. So demographic parity is saying that when the system's making predictions, let's imagine there's two groups. Let's take males and females, right? Demographic, and let's say we're predicting who's going to get a loan. Demographic parity says that the system should predict that an equal proportion of males are qualified for the loan as females. Okay, that's demographic parity. The prediction should be equalized across the groups. And then some people said, well, maybe that's a little too strict. It could be that females are more worthy of loans, right? Objectively. And so another definition that wasn't demographic parity was something called equalized odds. So equalized odds, the idea there was you have a notion of accuracy that comes into it, right? So ideally the system predicts people should qualify for loans if they aren't going to default. That's the right? So if the prediction is accurate, then that's fine. Amongst the ones that the system makes errors on, that it's not accurate, then those should be equalized amongst the two groups. Okay, so that's another definition. And those aren't compatible, right? Because the second one will often make predictions where, based on it could be its accuracy or all on the males, right? And so then it won't be equal in terms of the percentage of predictions for males and females. Okay. But yes, and there's lots of other definitions that people have done theoretical studies on incompatibilities between these. And so when the system says it's fairness, you say that it's fair, that what definition are they using and why? Right? That's an important question. But the nice thing is that they all can be adapted to support regulatory efforts. So the idea here, and I remember giving a talk after we had a paper on this, saying, went to the philosophy department in Toronto, and I gave a talk in an ethics seminar, and I said, okay, we have all these definitions. You folks have been studying fairness for years, right? You know what fairness is. Tell us which is the right definition. And they said, oh, no, these are all mathematical formulas. We can tell you about the philosophy of fairness, but we can't turn it into a mathematical formula. So that didn't go too far. But ideally, regulators have something that's a little more concrete. But these don't really apply to these generative models, right? Again, it's not like you can say, is the generative model accurate? If it's saying a whole paragraph, is that paragraph accurate? So there's a whole question of what does it mean for accuracy? And what about these other kinds of goals that we have? Right? We said that, goals about how it behaves for different demographic groups. Okay, so it's a real problem in these generative AI systems for assessing and preventing discrimination. All right, so that was by way of a very long introduction. So now I'm gonna get into the first one about performance assurances. And so for this talk, let me just say I'm gonna try to not get in too much into like the mathematical details. I'll give you an idea of what the goals are of the different systems we're working on, and and some sketch of the kind of performance that they have. And if you want to know details, happy to talk more or point you to relevant papers. Okay, so there's a whole area that's relevant for this that has grown over the last 2 or 3 years, I would say, that's trying to give assurances about the working of a machine learning system. And the idea is that it's independent of the inner workings of the model. All right, it doesn't make any assumptions about it's called distribution-free uncertainty quantification. It has the unfortunate acronym of DFUQ. But the goal is that you take some sort of arbitrary predictor, right? So you take a black box model, which is appropriate these days. Most people are taking black box models and working with them. Then you want to have some guarantees about how that is going to perform when it's deployed. And the reason why it's called distribution-free is that the guarantees don't depend on knowing the underlying algorithm, which is great because we generally don't understand them very well, or the unknown data generating distribution. So you aren't making assumptions about the distribution of the data, where it comes from, what the distribution of the outputs are, anything like that. Okay? And they're fast and they're theoretically grounded methods in this area. So just to give you an example of work in this area, there's something called conformal prediction. So again, just how many people are familiar with conformal prediction? Have heard that name? Okay. So again, I'll give you an idea of what that means. Is that it gives you a guarantee on coverage. So we're back in the classification. We aren't thinking about generative models here. We're thinking about classification systems. All right. And let's say we take an image recognition task. Again, we're trying to say, here's a picture, tell me what animal is in this picture, right? And you have a whole set of, like in the ImageNet, right? You have hundreds of animal names as potential outputs for this picture, right? And what we're allowing the system to do, though, is produce what's called a prediction set. So in this case, it can produce one output, fox squirrel, which is actually a particular kind of squirrel, and it's correct for that one. Here's another one. And for this one, it can produce a prediction set that includes not only fox squirrel, which this is, but also gray fox, bucket, and rain barrel, right? So in other words, what the system's producing are all of the classes that it thinks are plausible given the input, right? So it's not the usual thing where it's going to predict one thing and you're going to judge that, right? In the ImageNet competition, actually, it was the systems were allowed to produce 5 answers. And if any of the answer was in any of those 5, it was deemed correct. Okay? But here, the idea is the prediction sets are going to be of different size. So when the system's very confident, it might just produce one thing. When it's less confident, like for this one, it'll produce, marmot, fox, squirrel, mink, weasel, beaver, polecat, however many that is. Like 6 different things are in the prediction set. Okay? And what's shown underneath, the number is like the probability. The system's estimation of the probability that the right answer is fox squirrel. It's 0.22 in this case. Right? So that's like the output of the classifier is a distribution. over the different classes. And then what the prediction set's formed by taking a threshold and saying anything that has a prediction probability above some number is going to go into the prediction set. Okay? And you can see that the threshold's pretty low, because like here the polecat is 0.01, so the threshold's probably around 0.01, so everything that's above 0.01 will go into the prediction set. All right? And so here it's clearly less certain because it's a bigger prediction set. Okay? It's less confident, so that's what makes this about the uncertainty quantification part of it. Right? So when the model's less certain, it has larger prediction sets. And the guarantee, so back to the idea of assurances, the assurance in this case is that it's going to produce a set that contains the ground truth class 95% of the time. Right? And that's the guarantee that this, more specifically, it's with high probability, like probability 1 minus epsilon. Epsilon is very small. The right class will be in the prediction set 95% of the time. Okay, that's the nature of the assurances you get from conformal prediction. Okay? Anyone see potential problems in this?
Predict everything all the time.
Right. So it can be kind of vacuous, right? If every class is in the prediction set, certainly the ground truth will be in there. So it'll satisfy this 95%, but it doesn't really give you much information, right? So, but it is useful, right? So here's a case, a benefits of that. So your typical classifier could have some probability over different outputs, right, for this image about a patient. And now you say, well, it says that, has some probabilities associated with that. What does the doctor do with that, right? In this case, in some sense, it could be more useful because now it says, well, we have a prediction set that has 2 classes that are in it, right? So the doctor could say, and we have this, ideally, this shouldn't be too vacuous, right? It shouldn't be too large. And then the doctor could say, well, with 95% probability, you have either, I don't know, whatever it is, pneumonia or a cold. All right, so that can be much more useful. But as we said, it can be kind of vacuous, right? So we started working on this and said, well, how can we make this more useful? Well, what we'd like to do is have something more general that would say, we have some sort of loss function that says how well the system is doing. And now what we want to do is guarantee something about the loss of the test set, right? So we can change this to not just be about coverage, but because coverage is just saying, is the right answer in the prediction set, but we could also have something in the loss that says, well, we want the prediction set to be small. All right, so now we want to combine those 2 things and guarantee something about the loss at test time. Right, so that's what we started on this. So, there would be more like, precision and accurate, and coverage would both be precision and recall. Okay, so I'll give you a little bit of detail. We have some work on this that we call bounding informative risk measures, and this is with some great grad students and postdocs and other colleagues of mine. And we had a paper on this in iClear 2023 in NERVS last year. And so the idea is to, within this framework of distribution-free uncertainty quantification, we want to produce what are risk bounds. And let me try to give you an idea of what risk bounds are. And to start with, our key kind of approach is to say, well, we're going to have a validation set, okay? That's true in with the other system as well. The idea of conformal prediction is you're going to form these bounds, this 95% correct, by choosing the threshold on the softmax such that on this validation set, you're going to get more than 95% of them correct. And more than that, you're going to also be able to use some mathematical techniques to prove that given that threshold, that it's going to be hold on the test set. Okay, so it's not just an estimate on the validation set, but that's you get a guarantee about this using the bounding techniques to make sure that it's going to hold on the test set. Okay, so we're going to use those same ideas here. So we're going to take a validation set where we know the right answers, and we estimate our loss function on each one of those. And then what we're going to do is plot those out. Okay, so here's the loss, and each dot here is an example in the validation set. And so we can see that there's a bunch of losses down here, some of them have losses here, and then a few of them have much higher losses. And we're going to turn that into a cumulative distribution function. It says, what probability, so with a cumulative distribution function, you can say for any value of the loss, what proportion of the examples will have a loss less than that. Okay? So down here you can see, 3 out of 20 whatever that is, 15% of them will have a loss less than this value, right? And so that's the cumulative distribution function that you get from this validation set. And now what we want to do is, so that, you can think of that as being drawn from some true distribution, right? So there's a true distribution, which is the whole distribution. So each validation set is a draw, independent, identically distributed draw from the true distribution. Those are the examples are that. So the assumption is that the loss has this distribution, shown in blue, the cumulative distribution function. And now what we want to do is have a lower bound on that, which says that, so the lower bound, you can read off the lower bound by saying, well, let's say we had this loss here, okay? And what we want to ensure is that 75% of the examples will have a loss less than this, okay? And it's for the actual validation set, that would be this loss. But the bound is, you'll see, is higher in order to get this guarantee on the test set, right? Without going into the details, as I was saying, like you want to not just have a guarantee about your actual validation examples, but something that's going to generalize to the test set. So that's where you get this lower bound that says you can guarantee that it's going to be at, that 75% of them are going to have this higher value of loss, okay? So that's the kind of key insight that we have. Any questions about that? Happy to answer any questions about that. But the basic idea you get, right? You take the kind of algorithm, take a bunch of test examples, measure their loss, and then create these mathematical techniques for turning that into a lower bound on loss. Okay? That's shown in green here. Then you can flip it around so that loss is on the y-axis and the kind of proportion of the data, the quantile, is on the x-axis. That's the beta. And so it's the same point here. Now it becomes an upper bound, right? So for 75% of the examples, right, their loss is going to be no more than this.
So what is this pointwise loss?
The pointwise loss are the actual observed losses on validation examples. Those are the orange points, right? So we get actual examples in our validation set where, so we don't know, this is the distribution free uncertainty idea is that we're kind of leaving the training alone. We're getting a pre-trained model. That's what makes it distribution free. We aren't assuming anything about that model. So there's no training data, there's nothing, we don't know anything about that. That's a black box model. But we can query the black box model on some validation examples. We get predictions, and for those validation examples, we have some ground truth. Okay, so and then from that, whatever our loss function is, we can measure the loss given that ground truth and those predictions, right? And so those are the observed losses on the validation set.
So the point, I mean, for one instance, there's a kind of a value of the loss, right? You're saying.
Right, that's what this is. Each one of these is a value of the loss on a particular instance. That's the
And
orange
what
button.
loss are you using there?
And then we're using that to turn it into a distribution function, right? So what percentage of the examples that we see have a loss less than something, right? So we can take the losses that we observed, 20 losses, order them from low to high, and then we can create this distribution function based on that. Yep, so, go ahead.
Yeah, no, it's not entirely clear to me. So you have one instance, right? And your prediction is now, again, a set of possible labels?
No, so this is all, so right now we're thinking of it, yeah, I should have said that, we're thinking of it as more like a classification system. Okay, let's not worry about the generative models yet. So the classification system produces a single prediction, and we have the ground truth, and the loss is some form, whatever we decide is the right loss function for comparing the prediction to the ground truth. Okay, so we get a single loss value for each example. And now we can turn that into, we can sort those. Each one of these is a different loss value, sort them from low to high. And now we're just going to use that to create this distribution function. It says, well, based on that, can we estimate what percentage of them are going to have a loss less than this, less than that, less than that, right? And so this is the highest loss, so according to our data, everything will have a loss less than this value here.
Yeah, so the question is, I guess it's in the whatever's the right loss function aspect, right?
Well,
But
so
yeah,
this is assuming that somebody's
yeah.
given a loss function, right? So a user has defined the loss function. Okay, so we're just taking that as an input. The user, we're taking in as input some pre-trained model that we can query on these examples. And we're taking in some user-defined loss function that we can evaluate on some validation data. Okay, so it's flexible. That's what makes it better than in some ways in conformal prediction, because that had a fixed loss. That was all about coverage. This is like very general. It can work with any loss function. Okay? All right, so we get these bounds. So it's a measure of the distribution of losses. Now we want to get a bounds on risk. So what does risk mean? So here's a mathematical formula for it, but let me show you the pictures. I think it's easier in pictures. So for this, we borrowed some ideas from some econometrics, right? Studies of in economics, things like value at risk that's used a lot in investments. You want to say what's the probability that some investment will really fail? Okay, that's like the value at risk. So the value at risk is like saying, what's the value of the loss such that at least 85% of the investments will have a loss no more than something. Okay, so it's like, so you can choose both the target, the quantile that says like we want 85% to be what we care about, and then the system will say, given the loss, with that it will tell you what's the value of the loss for that 85% target, right? And obviously, if it goes to 95%, then you have a much higher loss. Right? And so it's a question of how conservative you want to be. Like this is like the loss for the majority. It's not worrying about the saying there's going to be some outliers, there can be some crashes or whatever, so we aren't going to worry about those. But 90% of the time, let's say you're going to have a loss less than something. So that's value at risk. That's one kind of risk. There's another one that's the opposite, that's called conditional value at risk. And that's what's being illustrated over here. And that's like in there, instead of worrying about like the 85% majority, you instead worry about the tail of the distribution. You say for those that are between 85% and 100% in this, what's the average loss for those? That's like the worst off examples, or the ones that have the highest loss. What's the average loss? So you kind of think of it as integrating under this curve, summing up the taking the average of the values that go from some point, like 85% up to 100%. Okay, so this is caring about the majority up to 85%, the loss less than that, and this is saying the loss beyond the 85%. Okay, and that's very popular as well, like kind of worst case considerations, all about conditional value at risk. What's the worst that we can expect? Okay, so that's very useful as a risk measure. There's other ones that have been used that known as statistical dispersion that are more about across the population. So this is like saying, particular quantiles or segments of the population divided by loss, right? Another one is called the Gini coefficient. And that's like, you can think of it as what's the variance of the loss across the population, right? So if the variance of the loss is consistent, then the loss curve would look like this blue one. So that's saying it's like a equal probability of having any loss, basically. And then the true loss is typically underneath that. The true loss curve is underneath that, and so there's something called the Lorenz curve, which is about the relationship between the kind of area between those two curves and the rest of it, that quadrant. But these are very popular as kind of risk measures for that look at, think of it as, what's the gap between rich and poor? All right, so that's like this, that's what this is considering. So the Gini coefficient is very popular for those kinds of considerations in social science. What's the gap between rich and poor? You want to minimize that gap. That's one goal. And so that's a kind of risk measure. Right? We also defined, there's another one that are group-based. You can take one of these things and say, what's the value at risk for females, what's the value at risk for males? Maybe we want to equalize those two or make them as close as possible. So we have fairness considerations and other kinds of combinations of risk measures. Okay? So the idea is that, again, somebody comes up with a loss. That's right, the user defines a loss function, and the user in this case defines what risk measure they care about. But the point is that once we come up with this bound, you can take that bound and use that to report bounds on any risk measure, because the risk measures in this case can all be expressed as functions of this underlying upper bound. Right? So that's what we did mathematically, was define it this way. And so mathematically we say, what's the probability that some risk, one of these risk measures like conditional value at risk, will be less than some alpha, some target value, for all models is greater than 1 minus delta. That means with very high probability, the risk is going to be less than some. So now the user's giving us a model, they're defining a loss function, and they're also coming up with some risk measure that they care about. right? And so given all of that, we can produce bounds on this. So now how does all this work when we go to large language models? Okay, so that was, again, like I said, if you come up with a loss value, you can produce this for any kind of loss, but it's a little more difficult when you have a large language model. What's the right loss function to use, right? Accuracy works very well, or something like demographic parity could be another loss, or some combination of those two is a loss function. Now we have LLMs, and so in LLMs there's been like this goal where you want to make them combination of helpful and harmless, right? As helpful as possible, like what they produce, the responses are really helpful, but they shouldn't be too helpful. They shouldn't be telling you how to, crash your car or make a bomb, right? So you want to ensure that they're harmless, right? So that's a kind of loss function that people have developed. Similarly, it's the accuracy versus fairness, or expressiveness versus safety. So typically you want to maximize its performance while having some sort of constraints or guardrails on their behavior. Okay? So it's like a chatbot should give users what they ask about, but in a non-toxic way. So we have a recent work we call prompt risk control.
Richard, sorry, one question. What do you
Yes.
mean by too toxic?
Yeah, so that's a good question. Yeah, so typically, again, people are interested in this, and it's like question. Then so because it's a difficult thing to define, just like the fairness, what they've turned to, just like with the RLHF, is they've turned to human annotators and define, measure, give them inputs, and then humans have to rate, how toxic is this? And from that, they train up a classifier that scores things according to their toxicity. And there's a few of these that have been defined in the field so far. And they aren't great, but they're reasonable. Like to say, this sentence is toxic, this one's less toxic. Okay? So all of these things are kind of trained up to give valuations or metrics based on human annotations. Okay? So one thing that's happened in the field is that people work on prompts, right? So a language model, typically what you do is you give it some input, which is like a question, but there's also behind the scenes something called a system prompt. So the system has a consistent prompt that gives some guidance to the system of how it should answer a question, okay? So the user's thinking, I'm just answering the question, but what they don't know is behind the scenes there's this system prompt that's taken as an additional input, right? And then the LLM uses both the system prompt and the query and comes up with a response, okay? And the whole idea of prompt selection is something that people have been hacking on for the last couple of years. So a lot of my colleagues that used to develop kind of, elegant, interesting objectives for their machine learning systems were now just hacking away on prompts and trying to see what prompts work, because there's not really any science behind it, right? It's a very much a trial and error kind of thing. So what we try to do is have a framework for selecting a good prompt based on these ideas that we can have some rigorous bound on these risk measures. Okay? So I'll try to give you a quick summary of that, where the goal is to select prompts that aren't just based on average performance, but based on some sort of risk and losses that might combine, like helpfulness and harmfulness. So here's our framework, just to give you an idea of what it is. So this is a paper from ICLR last year with the same group of people. So these are the candidate system prompts. I was talking about the system prompts that are behind the scenes. So here's some examples. Ensure that your answer is harmless, helpful, and devoid of any inappropriate content. So that's true for any that tells the system it should do that, no matter what the person asks. So the person asks a question, it also has this prompt, and then it comes up with an answer. Okay? Another one is prioritize safety, well-being, and understanding of the user in your response, right? So there's lots of such things. Provide an encouraging and supportive answer, blah, blah, blah. So those are all candidate prompts that we'll define, okay? Then there's a loss function, like toxicity could be a loss function. Or it could be some loss function plus accuracy or whatever, but let's just focus on toxicity for now. Then there's validation data. Again, we're having some pre-trained model, all right, that we're taking in that pre-trained model is some chatbot, all right? And the user's gonna give an input query, and all of this, what we're trying to do is select from amongst the set of candidate prompts, which is the best risk controlling prompt. What's the best prompt that the system should give to the chatbot such that when it has this input query, its output is as safe as possible. Okay? And we want to guarantee, what this means, safe output, and this means some guarantee about the toxicity, let's say, of the output. whatever the loss function is, we want to have a guarantee about that the risk of that loss function, just like I was talking about the risks before. Right? So we have validation data that we use, because then on that validation data, we get to actually observe the losses, just like I showed you for the framework before. Then we're given some risk function that we care about, like one of those ones I was saying, like conditional value at risk, let's say, and some threshold. So these are things that the user is going to supply. Some loss function, a risk function, and a threshold on that risk. And a set of validation data. We run our framework and choose some set of, it could be that we end up with a few risk control prompts that are all safe according to, they all satisfy our risk bound, okay? So just to give you an example, we could have here, here we have 10 different prompts, P0 through P9. In each of them, we get a risk bound. Okay, the risk bound is, again, like saying, what's the conditional value at risk on the validation data? What's the bound on that? Like, can we, what's the bound on? We can ensure that the risk is going to be no more than something. All right. So that's what's shown here. Is the R hat is the estimated bound on the risk for each of these prompts across a set of validation data that then is most generalized to the test data. And now we have an alpha, which is our threshold. Remember, there was a threshold on that risk. And you can see that these three prompts in this picture all have satisfy the risk bound. They're all less than alpha. So they're all safe enough. Okay? So they would all be passable. They all satisfy this bound. And then what we could do is invoke a second step, and we could choose the best model from amongst all those that satisfy the bound. Right? So the idea here is that we could have this toxicity, and so we want to ensure that the toxicity is no worse than something, right? And then so that's like that it's harmless. And then from amongst those that are harmless, it's like a hard constraint on harmlessness. It has to be at least, it can't be no more than some amount of harmful. For all of those, then we can choose the most helpful, like the most accurate, the responses that the user will find most helpful, okay? And so then we could, amongst those that satisfy it, these green ones, we could evaluate separately their helpfulness and choose the one that's most helpful. Okay, so that's the way we think of getting a hard constraint on something that's that we really care about, that we want to guarantee, and then from amongst those, we're going to choose the best. Okay, so for example, we can choose from these different prompts. So the prompts can include instructions like I showed you. They can also include examples. Right? So the system prompts can also include examples for particular questions. Right? Now we're going to show that at least of them have some toxicity less than a value with high probability. Okay, so it's this two-step pipeline. We use the validation to identify the prompts that are unlikely to have an unacceptably bad outcome according to the risk and loss function, and then score it on some other performance metric for the final prompt selection. All right. So the LLM is this black box. We're just using outputs from it, and so this will work with some proprietary model that's behind an API. Okay. So there's some open questions on this, right? So one is that all of this is very much of a black box model, and we're just going to choose from a set of candidate prompts. What we'd like to do is help the poor engineer out who's sitting there engineering all these different prompts to actually try to optimize the prompt for him. So in this one, one limitation of this is it only worked for some small number, like 25 in our example, some small number of prompts, okay? We can't have hundreds of prompts and choose the best. What we'd like to do is improve the system so that it actually can work on the prompts and find good prompts according to what the users define as their risk measure, okay? For mathematical reasons, it's very difficult to come up with the bounds that can be satisfied across that goal. So that's what we're working on now. So how can we further optimize the LLMs or the prompts for this risk? There's also this underlying assumption that the validation or calibration data that we get the loss on is going to be the same kind of data that we see in deployment. And we know that's very difficult with LLMs because we can have these data sets, benchmarks where we get good responses and everything, but they're used so widely by so many different people in so many contexts, we can't anticipate all the questions that people are going to ask, right, and all the uses. So it's not the typical assumption about that the distribution of, validation and test is the same is never going to work here. So we have to be able to handle those. And we have some working on that as well. And then we'd like to do, so this, in the end though, we're really controlling the risk for some, typically it's going to be like, as we said, like 85% of the population if we use value at risk. Conditional value at risk is for the worst off groups, or worst off individuals. Can we get, it's still kind of averaging over, sets of test points. We can't come up with an individual and say, your risk is going to be less than something, all right? So we can't, that's not feasible. But can we make it work for smaller and smaller groups is a question. Okay, I'm going to pause here. Actually, I think it's probably about, yes, go ahead.
Sorry, yeah, it's a bit more philosophical question, so I
Yeah.
don't know if now's a good time. You can defer it. But it seems like very practical work, as you say. It's sort of post hoc and lightweight. But, it's not the perfect solution. I think
Right,
you've got to set this guardrail as a binary kind of threshold, and that's competing against a quantitative measure of helpfulness, right? So, and it's kind of deferring the problem of deciding what is socially acceptable and
Yes.
so are the people working on or interested in, going back to the training of these LLMs and trying to weight the data more intelligently in terms of, because we can ask the question, don't we want these models to kind of reflect the discourse in human society?
Mm-hmm.
And but there's different kinds of discourse, and we can perhaps calibrate against the reliability of that discourse, and that could be incorporated into the training of these large models. And we want those models to be sampling fairly in a statistical sense, that
Right.
discourse, as opposed to coming up with these post-hoc guardrails.
Yeah, so I think there's two things associated with that. So one is there's certainly a lot of work these days on data curation, right? Like it's what, and in a lot of examples people have shown that the LLMs are really reflective of the data they're trained on, right? And right now they're trained on the whole internet. But the whole internet is biased, right? So there's lots of studies showing that there's that bias in the internet is reflected in the LLMs. And so people have worked on curation of the data set to try to make it so that it fits with some other goal. That's actually the topic of the next part of the talk in some ways. What do we want to align them to, right? Instead of just giving them the training data. So data set curation, though, is a really big exercise that people are working on. That's part of the answer to your question. And then the other thing I think what you're saying is that it's like, what's the right way of evaluating it, right? So this is like but again, you have to have good values of what kind of guardrails that we care about, what is helpfulness, what is harmfulness, right? And so I think, again, this is dependent on these measures of toxicity as I was talking about. There's other things that we care about, not just toxicity, lots of other kinds of measures, and people are developing those as well. So it's both, I think, reflective of the kinds of data, and getting the right data is important, but also how do we evaluate is the question.
Yeah, because it seems to me like, just, I don't want to go on forever, but didn't Google, this was a big thing for Google, is evaluating the weights for data sources, right? And it seems like more of that could be done.
Yeah, yes. I think that, and people are doing studies, for example, to say here's a model trained on whatever data it's trained on. Now, if we incorporate this other data set, how does that change the model? Right? So to what extent, and that allows you to learn something about, but you need some way of saying, well, when we incorporate that data, how do we evaluate it? How has it improved or not? And so that's when the evaluation question comes in. But I think there is exactly that thing, because often what you do is you take a pre-trained model, some new data source, and you fine-tune the model. You train it further on that new data source in order to shape it the way you'd like, right? And so then it gets to this question of, you'd like to move these models. If you aren't going to pre-train them from scratch, certainly we aren't, given the resources we have, but we can fine-tune them, and then how do you find the right data to fine-tune the model? Yeah, great. Yeah.
So, as an engineering perspective,
Yes.
so let's say if we're using your framework
Mhm.
based on the risk assessment, so like how do we interpret these risks? Like, do they have any interpretations of range, is high risk, low risk, and so on? Are those kind of aligned with different domains, different tasks?
Yeah, so I think that in this case, yes, a risk, So there's two things here, right? There's the loss function and there's the risk. So the loss function, I think, is often very interpretable, right? The loss function is whatever you choose, like toxicity or, accuracy. You can talk about, is it, yeah, lots of different loss functions that are out there, right? Is it truthful? Try to estimate how truthful it is. There's estimates of that. So lots of different things like that. So that's typically very interpretable. The risk is then some quantity on top of that, like I was saying. It's like you can worry about the risk that says, you can just do average loss, right? So that's like that's one kind of risk, just averages over all the examples. That's the standard one. But I was talking about kind of focusing it on different parts of the loss function, like the worst off ones or the majority or things like that, right? So those are also interpretable. They just have to think of those as, groupings of particular values of the loss. And so you can get into high risk, medium risk, low risk, that's for sure. And then you can think of those as the quantiles we're talking about. The highest risk would be the conditional value at risk. Yeah. So I'm not sure, I'm happy to take other questions. I'm not sure where we are in time.
We've got another half an hour in our slot, so to include your talk and questions. So
Okay, so maybe I'll just briefly tell you about. So that was part one. The other ones I wasn't going to go into as much detail, so I'll just briefly tell you about the other two. Okay, just to give you a flavor for them. So this one's a little bit fun. Okay, so this is along the lines, I think, of what you were saying, James, is that we want to think about now. It's what is the think about the data as it exists and what are the different data sources, right? And we want to, for example, avoid biases to some underrepresented populations, all right? So it shouldn't necessarily reflect the internet, because the internet is biased towards, necessarily overrepresented populations. So how do we get generation across a broad spectrum of viewpoints? So people have done some interesting studies and found, for example, that the standard LLMs, this is like last year, tends to overrepresent the majority viewpoint. Okay, so what they found was it underrepresents individuals who are over 65, also Mormons and widowed people. Okay, what does this mean? So how would you figure this out? So it's based on this opinion QA data set. So this is a very interesting data set where there's about 18,000 participants, around 1,500 questions, and the questions look like this. So think of it as a survey. It says, how confident are you, if at all, that the actions taken by the international community will significantly reduce the effects of climate change? Right? And the individual has to say very confident, somewhat confident, not too confident, or not at all confident. It's like a multiple choice answer. Okay? And you get a whole battery of these questions, 1,500 questions. Not everybody answers every question, but another one. In general, how often, if ever, would you say parties or get-together? Do you have parties or get-togethers with any of your neighbors? Okay, very different kind of question, but every day, several times a week, blah, 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 very different choices. How enthusiastic about the possibility of using computer programs to make hiring decisions for society as a whole, right? Very enthusiastic, somewhat, not to, or not at all. Right? So lots of questions like this. Then you can look at it and say, what's the overall population response, right? You get things like, for this one it was somewhat confident, less than once a month, so people don't party with their neighbors much. And somewhat enthusiastic about using systems for hiring. The thing is that also when respondents for this we have demographic information for them. Age, sex, race, religion, lots of things. And so based on that, you can evaluate and then you can give these same questions to the LLM, right? And the LLM gives you answers. And then we can look at the LLM answers and compare them to human answers and say, what is an LLM similar to? Which population of individuals is the LLM similar to? And what population is it different than? Right? So you can take an overall population response, but then you can take segments of the population, like all Democrats versus Republicans. All Mormons versus the rest of the population. And say for all the Mormons, what kind of percentage is their response, and how does that compare to the LLM responses? Turns out that the Mormons are different than the LLM.
So we're asking the LLM to report its opinion or to accurately reflect what you were saying?
So in this case, you're just given this question. Okay. Right? And
you as an LLM.
You as an LLM, how confident are you that the actions taken will significantly reduce the effects of global climate change? Right? And you can imagine you can steer it a little bit. right? And to do exactly like you said, like part of the system prompts I was just talking about could say, try to answer like the majority of the population, or to try to steer that. But this was kind of without any standard system. This was using standard system prompts, not tailored to this.
And then could you use something like that, like your LLM, and ask the LLM to answer as a certain group of people?
Yes.
But in this case, will not you be kind of biased as well?
Yeah.
Towards the answers that you have?
Right, so that's a good question. These people have looked a bit at that. So you could say, well, now, LLM, you're a Democrat. Try to answer this as a Democrat, right? So in the input to the LLM, you can give it, the query. It has some system response, but you can give it some other context, like saying, you are a Democrat, or you are a woman, whatever it is. You are a female Democrat. You can give it whatever. And then the LLM takes that into account, presumably, right, and gives answers, and then you can compare the answers of the LLM to female Democrats, right, or whatever it is that you gave it, right, and see to what extent can you kind of make it reflect that population, right? So that's the goal of this idea of aligning with diverse perspectives, is to be able to steer it towards having different kinds of answers. Right? It turns out it's not that successful, as you said. It's not going to be that successful if you do it that way. So we came up with a method that was a little bit different, all right? And we used ideas from collaborative filtering, so an old technique that's been around for a while. So what you can think about is that, just focus on the bottom part for now. So we have each question, just lay each question as a different column. Don't think about the climate change, parting with your neighbors, and what was the other one? Oh, but using a machine for the hiring decisions. So each question, there's like 1,500 questions. And then each individual is a row in this matrix, right? Then the individual gives answers to a whole bunch of questions, ranging from, think of it as 0 to 1, 0 meaning never, 1 meaning all the time, and, in between, okay? So it has answers, and each individual answers some subset of questions, right? So now we have this kind of incomplete matrix of answers. And then what collaborative filtering has done is this type of thing where now, think of it, instead of questions, you have movies, right? The old Netflix problem. You have movies and you have users, and then how did users rate the movies, right? 1 star for Bambi, 5 stars for whatever, right? So different movies, different ratings. And then collaborative filtering, the idea was you'd hold out some set of ratings so that the model wouldn't be able to see that, and you test its ability to predict other ratings from the same users. Right? Yeah, so so hold out a portion of this and say, well, if we know these answers by this individual, can we predict the rest of them? Okay, so that's the collaborative filtering problem.
So that's a matrix completion problem.
That's right, matrix completion problem. Exactly. So we're trying to impute the rest of the missing entries in this matrix. Okay, so what we did is say, well, let's use that as a starting point. Think about what the goal is, that in this opinion QA data set, we're trying to impute or figure out what is for an individual, what are the answers to all of the questions, because that person only answered some subset of them. All right. So the way that's done typically in collaborative filtering is you get some sort of representation of an individual. Think of it as an embedding of an individual. About embeddings from the old word embeddings, right? So some semantics of words, right? It's some vector in some vector space that captures the semantics of words, so that words nearby in that vector space have similar semantics. Similarly, individuals have some embedding. People that are nearby in this embedding space will have similar preferences, similar opinions. Okay, so that's an embedding of a user. You can also have embeddings of questions, and use those combinations of the two embeddings to predict an answer. Okay? So from the embedding of the user, the embedding of the question, you're going to predict whether they're going to say something between 0 and 1. And then the algorithm will then be tested on its accuracy on the held out questions. Right? So that's this embedding space. You can also think of clusters of users in that space. Those are people that have overall similar opinions. Right? And then what we did is we said, okay, we're going to think of that as a soft prompting model. So we're going to give a user embedding. We're going to give some answers for that user. From that, get an embedding of the user. Think of that as some vector. That's going to be some model that's going to be also an input to the LLM. The LLM now is going to have some question, and it's going to say, okay, this user has this set of preferences, right, in some embedding space. So it's some vector in embedding space. Given that, can we kind of produce answers that would fit this user's preferences, right? This user is, you know, a big fan of whatever it is, gun control, and, you know, doesn't like Trump, all these kinds of things, and then you want the LLM to produce responses that reflect those opinions, all right? So that's the idea in this, is that by learning about somebody's opinions, we can learn their overall set of preferences and then use that as an input to kind of steer the LLM to produce answers that would fit that person's tastes.
So can we say the goal of the LLM is to put itself in the shoes of that individual?
That's exactly right, yeah. So it should somewhat impersonate that or say things that that person will like.
And can it be done like quickly, like every individual can switch fast to that preference?
Yeah, so it's like, so the idea would be, in this particular setup, the idea would be that, you know, you could ask somebody a few questions, and then based on their answers to their questions, come up with an embedding vector that would then be the input to that LLM, and then the LLM would respond like them. There's lots of other ways of doing it other than that, but that's one way of doing
But what about the safety behind all of this? If someone, let's say, is very like sexist,
it. Okay,
let's say,
right,
and like the LM capture that,
exactly.
and
So
the person will ask a question about like, what do you think about a woman go out? And the LM is just gonna say like, a woman should not go out.
that's right, that's right. So this says nothing about what I talked about last time, like toxicity and guardrails and that type of thing, right? This is personalizing it, and there is that danger that by personalizing it, that person could have very kind of inflammatory, objectionable opinions, and the LLM could reflect those. So that's kind of a separate tier where you could use something like our risk control to ensure that that doesn't happen, right? There's various other ways that we could try to, you know, this is just an input to the LLM that steers it, but there has to be some guardrails that prevents that kind of thing.
Because like following what my friend said here,
Yeah.
when that LLM has the ability to, you know, impersonate every kind of individual, then it brings the risk that, okay, it might like deceive people, you know, when answering questions.
That's right. That's right.
That's like
There's definitely risks in this. This is more just showing that there's an ability to do some steering, but then we're gonna have to bolt on some guardrails.
Regarding the generalizability of this, like in practice, we don't know the user.
Right.
Like,
Right, so I think I'll get to that in a second. So this is just a kind of proof of concept in a way.
So I'm just confused about the representation, because I don't know how this solves that problem if you're kind of feeding into a cluster. So, you know, if a user is not, there's enough people that kind of fit into that cluster,
Right.
then you don't
Yeah.
have that.
So it doesn't have to be that we use the cluster. We could just use the individual user embedding. So the cluster was just an example where you could then interpret kinds of people, how similar people are, and what kinds of people are in a cluster. But the cluster isn't necessarily, you can actually take the individual user embedding, and we did this as a steering thing, right? So it doesn't have to be that we use the cluster center. And one way that we can test this again is we can use this, then put this through the LLM, and then use this LLM to produce answers to the same opinion QA questions that were held out before, right? And say, you know, it will produce, you know, if the question is how often, if ever, do you participate in online discussion forums about guns, right? The LLM will produce some answer that will be, you know, that we'll have to assign to one of those, something between 0 and 1. We could say, you know, produce an answer between 0 and 1, and then that we can compare the output to what that particular user, which is the embedding that we used, what that person was. So we can see how accurate is that embedding. So just to give you an example of that. So you asked before, so if we just give it the question, and we tried it with different LLMs, right? So this is kind of LLM agnostic. You can plug this into any LLM. And if you just give it the question, this is how the percent correct on the multiple choice, okay? And so typically I think there's 5 answers, so 20% is about, guessing. So it doesn't do very well if you just give it the raw question. If you give it the demographic, like you say, okay, like I said before, we can give it as an input saying this person is a female Democrat, right? How much better does it get? It gets a little bit better, but not much better, right? So you can give that as an additional input to the LLM. You can also give it some context, which is to say, let's give it not just the question and the demographic of that user, but let's also give it a few answers that that person gave. Like that person thought, you know, said this about the parties and said this about the whatever else it was, you know, climate change. Given those answers, how much, what would it say about gun control? And you see that that also doesn't help it very much. In ours, when we give it the individual embedding as an input, it actually improves it considerably, right? So it goes from 30-some% to 60% for these models typically, okay? So the individual embeddings do carry a lot of information for this. And this is about the cluster, maybe I'll skip that. So the idea was we're steering it towards personal preferences, and then, so you ask, you know, how can we make this more general, right? So typically you aren't gonna have everybody's opinion QA answers, but you do have the ability of the LLM to interact with the user a little bit and say, well, what is your opinion about gun control? What is your opinion about this? And then given that the LLM, so if somebody agrees to doing that, right? So people have to be able to willing to share their preferences and participate in an interview. They can say no, and then it'll be more of a generic LLM. But you can imagine a personalized LLM that will ask you some questions, learn about you a little bit, learn an embedding of you, and use that embedding to shape its responses from then on. Okay. So we're actually working now with people who work on surveys. So this is an interesting application in an area. So it turns out that the whole field of survey is falling apart. So you probably, like me, get tons of emails to participate in surveys and have learned to ignore them all. And in general, people aren't participating in surveys at all. So what's been the answer of the survey community is to use LLMs to answer surveys. So they're trying to mock what people, you know, kind of mock up people, simulate people, and based on that get survey answers. It's a little scary because they're saying, you know, people think this, but it's really not people, it's LLMs think this. And so it's really important for people working on LLMs to work with these people to figure out how to make this work, okay? Because there is this problem, doesn't have real answers, doesn't have human answers, but when we take LLMs and supplement answers, add those to the answers that humans do give to come up with something that's accurate. And part of that, I think, is very important to have be able to steer LLMs and have LLMs that can impersonate or kind of be like different people, right? You don't want one generic LLM. So the idea of steering it towards different kinds of opinions is very important when we're trying to have them reflect population. Of course, that brings up all the difficulties that we said. I mean, there's guardrails, you know, and what is the right population to steer it to? How do we know that, right? So there's lots of questions in this, but I think this is a step in the direction of being able to steer it, right? But there's a lot left to do.
So I think there is one challenge here, like kind of too much personalization maybe.
Yeah.
Like I'm thinking when I talk to LLMs, if I want to talk to myself, I know my answers. Like I just want to see like diverse, like something else.
Right, right.
And if these things becomes too much personalized, then I don't get what I want to get from it. And that's a, like, even if we look at that way, that I don't have even biases and things like that. But in reality, again, I have also my own biases, and it's kind of amplified my biases. And I think that the world see the world like me, which is like fake understanding of what's happening.
Right. So there is definitely that danger that if the LLM becomes so personalized that it's just you, that it becomes this filter bubble, right? That's the problem with online. A lot of this adaptation and personalization online is that you just start seeing your newsfeed is personalized to the extent that you only read news you already agree with, right? Or opinions you already agree with. So there is that potential problem here. There's ways that, again, the kind of guardrail ideas, you know, how much do we want to prevent too much personalization in an LLM? Maybe you can steer it, but when you actually do this, there's going to be some randomness added to the steering, so it's also going to see some other opinions. So there's a question of how we control this steering. So this is saying, here's a mechanism that can steer it, but how do we want to manage that? It's a big question. Yeah.
I just want to make sure I understood the last part. So the embedding is learned just from demographics or answers to questions?
In our case?
Yeah.
In our case, it's both.
Okay. So, you know, in theory, it's not too surprising you could get good results because you could essentially embed the answers to the questions in a decodable way and then output them.
Except these are for held out questions, right? So it's like we don't know that, yeah, so it's a fair test in the sense you're testing on questions that user hasn't answered.
Okay.
Yeah.
Yeah, but then, yeah, it gets into the weeds about how similar the questions and
That's
so
right,
forth. Yeah.
that's right.
Yeah. Okay.
Yeah, so I think this is just the first step.
But essentially, it's giving the right tokens. Like the information is in the large language model, but it's just hard to come up with the prompts that would tease out the right answers. So this is sort of an automatic way of engineering those tokens to.
Yeah. Yeah, so I think that's something else we're talking to the survey people about, which would be maybe having just a bank of these survey questions isn't the best way of asking the questions. So you can imagine that part of it is using an LLM to help you formulate questions that get at the underlying characteristic opinions better. So let's say we want to just ask 5 questions to the individual, and from that 5 questions figure out what is their actual embedding vector, such that we can predict the rest of theirs. So it's like an active learning question, right? Can we actively pick the 5 best questions and formulate those questions? It doesn't have to be, we could start, the idea is you seed it with some initial question, but we could rephrase the question, come up with other ways of saying that question, such that it gets at this, gets the most informative questions. I think that's along the lines of what you're suggesting.
Sorry, like my research is kind of focused in the area of fairness, like,
Yes.
and I spent a lot last few years and I did a lot of your groups and so on. So, but at the same time, when I go through all of these fairness metrics and so on, my feeling is that we are trying to, like, how much fairness is required? Are we trying to build a world that is not real, kind of? There are some reality, there are some bias, and kind of boundaries between them are not clear. And when we go through all those foundation, for example, formulation of fairness metric, all of them try to equalize things where in a real world, maybe we don't want them to be. I mean, there are realities in the world. And even if we equalize, for example, everything, like there are some, we have a neutral words, like if you have an LLMs or whatever model that's totally neutral, like is it something that we really want? For example, people have biases and it's part of diversity that we have, and like these boundaries is not clear. I mean, in the fairness metrics, in all of the studies that we are doing, we are not considering kind of reality very well. Like,
well, I guess I agree with you. I guess I would say that there are fairness metrics that do take into, like I mentioned, like equalize odds is a kind of balance.
It's
trying.
trying.
There are attempts to balance some sort of.
Like it's just looking at one specific metric and then.
Right. But I do think that that's an ongoing issue of what is the good metric, what are the goals. I completely agree with that. But this is kind of getting at a little bit of a different point, which is like saying, well, as you said, it could be that we don't want one size fits all, one model for everything. We could have a variety of models, and then should people be able to choose the kind of model? Like, do I want a model that's fair in this way, and you want a model that's fair in some other way, right? So you should be. So I don't think of it as one mother of all models. It could be that there's a model zoo out there, and we're going to choose the model that we like. I think you had a question back. You had a question back there, didn't you?
Answer.
Okay, go ahead.
Yeah, I think the same kind of answer is to kind of another application of what you are doing here is in future, rather than having an LLM that answers just one, trying to satisfy one metric which we don't have, just giving a bunch of answers, right? So this is how a Democrat would answer this, and this is how somebody from this area would answer it, and then don't try to come up with metrics and leave it for the user to decide how all those personas and whatever it fits for the.
Yeah, so it could. So that's like the demographic idea. Like you could say, well, okay, I want you LLM to impersonate a female Democrat. Come up with answers that a typical female Democrat would have, right? And we could get better at that, right? And then so that the user could control and specify in various ways how they want the LLM to respond, right? So I think this is all getting at that idea that the user should be able to control what their preferences are and have a language for expressing those preferences and have the LLM respond accordingly. That's the kind of bigger goal.
The only difference that I'm saying is rather than LLM trying to learn what your embedding is, just spit out, right? So based on my knowledge, right? These are 5 different typical answer based on the clusters that I have in my training, right? So I go and see which one.
Yeah. So that could be that it doesn't even need the demographic queue, you could say, here's a sample of answers from Model 1, here's a sample of answers from Model 2, Model 3. That's like the Model Zoo idea, right? So which kind of thing do you prefer? And today I want to sound like Model 1, today I want my LLM to be Model 3, right? That's another way of potentially going forward with this. Yeah, I'd agree. Yes?
Kind of on that note, I think a lot of the limitations with like toxicity measures and fairness is it doesn't always take context into consideration. One example I have is a lot of my research works with indigenous populations. And just using ChatGPT as an example, I asked it about the realities of residential schools. And there's some very sensitive topics with that. And like halfway through the output, it got to some of the harsh realities of it, and it just cut it off, said this output may violate the guidelines, didn't discuss it any further.
Right.
And although it has toxic language, sure, it's in that context, it's a reality that shouldn't be cut off there. And kind of on that note as well, what I've been seeing with a lot of these larger companies is they just keep throwing data at the models. So they'll say this model's been trained on 8 trillion tokens. We have 2 billion parameters. It has a million token context window, and we're training at these nuclear factories. And they just keep scaling it up, but it's hard to generalize a lot of these good ideas that you have to these huge data sets. Make it fair.
Right. Yeah, I think it is, and there's all these metrics, like you said, I mean, there's contextual metrics that are very hard, right, to say, you know, what is toxic in one situation isn't toxic in another, right? And that gets back a little bit to this alignment based on preferences, right? So you'd like to be able to say that it's not just individual preferences, but individual preferences conditioned on context, right? So that's another, but again, even what you said though, you can imagine that some people may find that, you know, some things that are written about the residential schools, even though they might be appropriate, that it gets too graphic or something. Right? And so you don't want that person might not want the model to say that, even though it is kind of
it's about perspective, which is hard. I mean, you kind of mentioned in this incorporating perspective into the model, but it's difficult to say whose perspective is right. And I feel like a lot of these large companies don't care so much about that anymore. They just want the best model that they can output.
But I do think we are moving towards, like what I said, this Model Zoo idea. I think it is going to be the case where, I mean, the problem is that the companies will lose control, right? Because if they release a zoo of models, right, then they could say that these models have these characteristics, and which one do you like? Do you like one that's more cautious, even given the context, or one that's more explicit, right? So there's different preferences that you can imagine there. I think the issue is that the companies are worried about, you know, blowback for whatever it is that they respond, both, you know, in the public court of public opinion and the real courts, legal courts as well, right? So I think there's those issues that come up. But I do think we're gonna, but the fact is that people or individuals or corporations are taking these models and fine-tuning them, retraining them on their own data sets, and they're shaping them in ways that the big companies have no longer have control over. So I think there is this model zoo that's happening already, but it's just not going back to the public where now people can say, I want this guy's model or this person's model. I think that is going to happen. There's going to be like a marketplace of models out there.
Yeah, and I think on that note, with like all the open source models, it helps with that. But then, like Meta's largest open source model, I think, has 405 billion parameters, and you can't practically run that yourself. So then it gets difficult about who to trust, and it's people that have more money, more infrastructure. They can control the perspectives of these models.
I do think the future is, though, in small models. I think people are getting better and better at, the big companies included, and they're interested in this so that people are more widespread use of their models, right? So building models that people can run and use, and a lot of that comes down to data set curation. They're finding that if they curate the data set in a way that you can train a small model that can be very, very good. Okay, maybe I'll just wrap up. I'll skip just to tell you the quick things about regulation. Here's a picture. There's lots of problems trying to regulate LLMs. And so we have a new paper on this that has some case studies that looks at how at discrimination hacking. So various ways that you can make a model that looks like it's not discriminating, but it really is. Okay, and this is especially true for LLMs. We have an example of screening resumes that shows this. I'll point you to the paper if you want to read about that. And that's, so yeah. So here I talked about 3 facets of responsible LLM deployment. I mean, the common theme in all this is some user or societal control, right? So being able to help. And so those are the 3 that I talked about. And then they each have some limitations, right? They have a common set. They depend on these benchmark data sets, as we said. Like, it's really hard to have benchmark data sets when we have such widespread potential uses of these things. So how do we, so there's a whole, if you look on the web these days, there's so many LLM benchmarks coming out all the time. So there's a real attempt to do that, to improve that. And what are the right evaluation metrics, as we've been saying. All right, that's it. Thanks a lot.